class number 3 of the physics of sound, covering today forced oscillations. Forced oscillations are as common as free running. As a matter of fact, they can both happen at the same time. The road drives oscillations in the wheel suspension systems of automobiles, trucks, and buses, like this one. Also, oscillations in the cone of a loudspeaker are forced by the coil in a magnetic field. But a forced oscillation scenario can be as simple as this. It is not unusual for a free-running oscillation to become the driver of another. In this case, a heavy pendulum is driving lighter ones. To illustrate one of the most important concepts you're going to find in this topic, resonance. Okay, let's get down to business. Adding forces on mass m resulted in this differential equation. However, there could be a driving force acting on the system, in which case the restoring and damping forces can no longer add to zero, but to this driving force, resulting in this other differential equation. Introducing the same and simplifying definitions that we use for the free running case, the equation reduces to this one. And it also has a name, the second order non-homogeneous linear differential equation. Forced oscillations also happen in electricity. This is the driven serial LRC circuit, and it's described by the same equation, where the gamma is R over 2L and the angular frequency is the square root of 1 over LC. There's also the parallel circuit, which has the same equation. It is driven not by a voltage source, but by a time-varying current source. Here, the attenuation coefficient is 1 over 2RC, and the natural frequency, same as in the serial, is the square root of 1 over LC. Well then, it's time to solve the non-homogeneous equation. Any function that's periodic in t may be expressed in terms of a Fourier series. Using the exponential notation, it looks like this, where the amplitude of the force components, f sub n, are the integral over the period of the force. So solving the equation for the case of the sinusoidal driving force solves for one of those force components, the general solution being the sum of all the solutions.
Then why mess with these complex numbers when we could use, say, f by cosine of omega t?
Your question makes sense. We could use that. But then you will hate the algebra and the trigonometry. I hate that too. Just trust me. Now it's when knowing that solutions to linear differential equations are unique, we suggest one. And from the magic hat, this comes out. When solving for the free running case, it was found that if lambda 1 and lambda 2 had these values, then the left-hand side of the differential equation would be 0 for all t. All we need to do is find c so that when operating upon, it becomes equal to the force. Then being that a solution, then it's the solution.
That's it? No physics? Just math?
Oh no, there wasn't physics out of the magic hat. When the force starts acting, there will be a free-running transient process due to the disturbance. There. After the disturbance response dies out, the system must keep dancing at the rhythm of the oscillating force. There. So let's find c such that makes the expression below true for all values of t. Taking the derivatives and factoring out c by e to the I omega t, taking modulus on both sides, being the modulus of e to the I omega t equal 1 for all t, the expression for c becomes, but c is the amplitude of the force oscillations, x sub max. And what have we got here? Resonance. The main feature of this expression is that of having a maximum, which is the resonance. At omega equal the natural frequency, the expression reduces to this one. However, the real maximum happens at a slightly lower frequency, but in practice, the resonance can be considered to occur at the natural frequency. For very low frequencies, the amplitude equals the static displacement of the spring under the applied force. The quality of resonance is defined as the ratio of the oscillation amplitude at resonance to that static displacement. A little, actually very little algebra renders Q in terms of the oscillation parameters, omega sub 0 and gamma. Let's get back to a solution for the steady state. We can cancel the exponentials and the expression takes the form. The left-hand side must equal the real number f over m, which is saying that it cannot have an imaginary part. So allow the complex number c to be expressed like this. Alpha would be the phase difference between the response and the stimulus. The imaginary part of the above product must equal 0. Rearranging, resulting in this elegant expression. Here's the plot of the phase difference alpha as a function of the angular frequency omega. Notice that for very low frequency, x is in phase with the driving force. For very high frequency, it is counterphase with the stimulus force. At the natural frequency, the phase difference is exactly 90 degrees or pi over 2 with the driving force. Physics, please! Okay, fair enough. Here's some experimental proof. A mass spring system is pumped up and down by a motor. At low frequency, the response shows clearly in phase with the stimulus. As the frequency increases, the response lags behind, and at resonance, it becomes 90 degrees out of phase. Beyond resonance, the response lags further and further, approaching counterphase for frequency way above resonance. So we have the steady state solution when the force was F by E to the I omega t. Had the force been F by E to the minus I omega t, then the solution would have been this one. All these forces with imaginary parts have made our life less miserable by easing up the algebra, but it's time to get real. Fortunately, that's easy.
I got it.
Half and half, I guess.
That's the Euler's
Yes,
formula.
Sebastian.
E to the I theta equals cosine of theta plus I sine of theta, right?
Yes, you're right, Sebastian.
The solution is now the sum of
Oh
both
my God.
contributions. A cosine is our result, right?
Yes, Sebastian, you're right again. And now we're back to the real world. Now that we have real forces and displacement, we can talk about power, which is the work against the friction forces per second. That equals the product of the force by the speed. Also, friction forces are proportional to the velocity of the x derivative against t. That's why the velocity shows squared. Now we may replace x by the general solution we obtain to get an expression for the power as a function of time. Here's a chart showing the power peak values and even the time shift due to the stimulus to response space. The chart makes it obvious that the average power is half the peak. Finally, replacing the amplitude by its expression in terms of the angular frequency and oscillation parameters, we get the expression for the power in the same terms. This function is the one called the Lorentzian. And Lorentzians are bell-shaped curves in this type of chart known as the frequency response of a system. Lorentzians peak at the natural frequency, no matter how much damping there is. We have arbitrarily chosen 100 radians per second for omega sub 0. The power peak has this expression. If we assume, very arbitrarily, that f squared over 2m equals 1, the peak comes equal to 1 over 2 gamma, which stresses the fact that it's inversely proportional to damping. And here comes a very important definition: the width of the bell at half the peak power. It's known as the bandwidth. And if the bandwidth is much smaller than the natural frequency, then it approximately equals twice the attenuation coefficient, in radians per second, of course. You do the algebra, it's not that tough. Now we multiply and divide by omega 0, and what do we have here? Remember Q? It's a resonance quality. So the bandwidth is the natural frequency over the resonance quality. So for gamma equal 2, the Q is 25 and the bandwidth is 4 radians per second. For gamma equal 4, for gamma equal 8, and surprisingly, the approximation is still good enough even for gamma equal 16, being the bandwidth only 1/3 of the natural frequency.
What about the transient process?
You're right again, your nerdiness. That still needs to be addressed. For that, we need to bring back the general solution we pulled from that magic hat. That one. Where A and B depended on the initial conditions. Now we use the real steady-state solution and change A and B to get a real version of the transient part, assuming that omega sub 0 is greater than gamma. Instead of determining A and B from the initial condition, it's going to be easier if we try all the two arbitrary constants, say A and B. We will further assume that the force is driving the system at its natural frequency, so omega will be equal to omega sub 0. And we get this. Are we ready for some initial conditions?
Yes!
I was not talking to you, Sebastian. I was wondering about the rest. Say the system when t equals 0 is at rest at x equals 0. So we make the t's equal 0 and the x equal 0 to get this equation. The solution of which is obviously a equal minus x sub max and b equal alpha. But at resonance, or at the natural frequency, the phase equals pi over 2, or 90 degrees. Remember this? The particular solution for these assumptions and initial conditions is...
Yes, I know that.
Oh,
the
God.
cosine of an angle minus pi over 2 is the sine of an angle, right?
Sebastian, that's high school stuff. Now we all know that you earned your diploma, right? For reasons that will become clear, allow gamma to be 1 over tau. Then the above becomes... Tau is the response time of the system, or how long to reach 2/3 of this steady state, approximately 2/3. Let's plot the solution for several values of gamma, or tau. Same as when the amplitude was plotted against frequency, it was called the frequency response. This plot against time is called the time response of a system. These assigned functions modulated by exponentials, and it shows the tau of 1/2 a second when gamma equal 2. When gamma equal 4, it shows 1/4 of a second, 1/8 of a second, and 1/16 of a second. Funny, tau is response time, while the time response is the whole chart. And finally, here's the cherry on the cake. On one hand, the bandwidth equals 2 gamma, always slightly greater. On the other, the response time, tau, is 1 over gamma, also greater, 2/3, remember? So the product of tau and delta omega must always be greater than 2. Why the tada? Because it is an important result. The smaller the bandwidth, the slower the response. The more you know about the frequency it responds to, the less you know about the time response. This shows up time and again in physics and technology, with different magnitude pairs. The greater the radar bandwidth, the smaller the uncertainty in the position it determines. That's why the bandwidth of long-range radars are narrower than those for short-range missile guidance. Another curiosity is that the smaller the bandwidth, the bigger the antenna. Here's another one. Laser light is almost perfectly monochromatic, meaning very little uncertainty in its frequency. But that is as long as it remains a continuous beam, one that started very long ago and very uncertain in time. However, the frequency becomes uncertain with short laser bursts. Those kind of compromises were faced time and again. Yet, it was not until quantum mechanics that it got a name, the Heisenberg Uncertainty principle. As we saw, it happens that the smaller the uncertainty in the energy of a photon, which is proportional to its frequency, the greater its time uncertainty. Energy is said to be the conjugate momentum of time. In a cathode ray tube, like the ones used in old TV sets, the momentum of the electron beam could be determined with very little uncertainty. But not so the position. But when electrons are confined into tight spaces, then the momentum becomes uncertain. Position and momentum are conjugate as well. Well, Sebastian, do you have anything to add? Nope. Then we are ready for the quiz. Well, here's the quiz. The answers can be found at the end of the video. First question, part A. Obtain the expression for Q in terms of L, R, and C for the series circuit. Yes, Sebastian, I know what you're thinking. Save it. Part B, obtain the expression for Q in terms of L, R, and C for the parallel circuit. Problem number 2. In practice, the main power loss in a resonant circuit is the resistance of the wire in the coil. Prove that the two high Q circuits below are approximately equivalent near resonance if the uppercase R equal Q squared by the lowercase r. Notes: being equivalent means that the power source cannot tell if it's one or the other. And when dealing with electricity, the imaginary unit will be J instead of I. That's already used in representing the intensity of the current. Problem number 3. Very soon after sound began traveling the wires as an electric signal, hiding inconspicuous beeps for synchronizing event with those sound signals has been used time and again. These beeps are then detected by narrowband tuned amplifiers. Say the detection threshold for triggering the event is at half the maximum output, and the bandwidth is 20 Hertz. How long has the beep to be? And finally, problem number 4. Why is it that you can keep swinging by pumping your legs? Here's a hint. Same happens when you pump the capacitor whenever it's fully charged. L and G in the pendulum, as well as C and L in an electric circuit, are called the oscillations parameters. That is why, when oscillations are forced by altering them, it is said that you have parametric oscillations. After this, we are ready to start with the waves. We're getting there. Subscribe to the channel. If you need to see the answers, stay with the video. They're coming next. Only after you have answers of your own is that you can take a peek at mine. Here they are. Let's obtain the expression for Q in terms of the L, R, and C in the series circuit. First, we must remember the expression for Q. Then, the attenuation coefficient and the natural frequency. Now we do the algebra. That's it. But there's another interesting definition here. The characteristic impedance theta sub 0, which is the square root of L over C. That definition allows to express Q as the ratio of this characteristic impedance to the resistance in the circuit. Now we obtain the expression for Q in terms of L, R, and C in the parallel circuit. We recall the expression. We bring attenuation coefficient and natural frequency into the mix, algebra, and the answer. We can also express it in terms of the characteristic impedance. Notice that it comes out as the inverse of the case of the series.
Just as I thought, a piece of cake.
Sebastian, we are just warming up. For the second problem, we need to prove that the two high Q circuits below are approximately equivalent near resonance if uppercase R equals Q squared by the lowercase r. To be equivalent, the power source cannot tell the difference, so the voltage across it must be the same. Applying Kirchhoff's law for the currents, rearranging, near resonance, high Qs allow neglecting the voltage across the resistance as compared to that across the inductance. So I sub L is approximately equal to the integral in time of the entire source voltage V over L. Let's replace I sub L. About V, we already know the solution to the differential equation. so we can replace all the V's with it. That results in, let's make another replacement. These two cancel each other, which means that at resonance, the current through the capacitor is equal and opposite to that of the inductor. Finally, we get to this expression. Whatever is dividing the voltage and rendering a current is a resistance, and that there is the resistance of the circuit at resonance. If we divide and multiply by R, that there is Q squared. And so, the requested has been proven beyond any reasonable doubt.
Question.
What, Sebastian? Don't you agree?
No, I do agree. But had there been a resistance in parallel to the capacitor, wouldn't a small resistance in series be also equivalent?
You mean like this?
Yes. Does the same relation hold?
Yep, it does. You know, Sebastian, that was a good question. Problem number 3. Being the detection threshold for triggering the event at half the maximum output and the bandwidth 20 Hertz, how long must be the beep? So the trigger threshold is half the maximum signal. Then, if the beep is longer than the response time tau of the amplifier, we're good, because at that time it will already be 2/3 of the maximum. We know that no matter the technology on that narrowband amplifier, this will be true.
That's the Heisenberg Uncertainty principle.
You're giving me a run for my money, right, Sebastian? So tau must be greater than 2 under delta omega. But delta omega equals 2 pi per 20 Hertz, which comes down to 62.8 radians per second. Then tau must be greater than 2 under 62.8. That's approximately equal to 32 milliseconds. The beep must be longer than 32 milliseconds. And finally, why is it that you can keep swinging by pumping your legs? Let's check that hint first. The energy in a capacitor is 1/2 Q squared over C. If you pull the plates apart when charged, the capacitance lowers, but the energy increases. It's not that energy is coming from nowhere. The force that separates the plates must work against the attraction of the field within. The initial plate separation is restored when the capacitor has no charge, and since no force is involved, no energy is taken from the system. In this case, the pumping frequency is twice that of the oscillation. This maximizes the parametric effect, but is not necessary. It may be pumped maybe once per cycle, every 2 cycles, and still stay oscillating. It all depends on how much damping there is. Now let's go for the swing. The potential energy of the swinger is inversely proportional to L, which is the distance from the pivot to the center of gravity. If the legs are pumped when the swing is at its highest, the center of gravity is pulled to a smaller L, thus a higher energy. That is, the muscles working against gravity. The L is restored when at its lowest. The process is usually repeated at the other end, happening twice in every cycle. However, the legs may be pumped only once or even once every 2 swings. Though not at its highest, it will still go on.
That's all, folks.